The world of robotics is entering a stage once thought impossible. Machines that can see, think, and move like humans. At the center of this revolution lies one of the most intricate engineering challenges ever attempted, the humanoid hand. A simple gesture that humans perform effortlessly, like picking up a glass or tying a shoelace, takes years of research, thousands of sensors, and highly advanced AI models to reproduce in robots. Today, companies like Tesla, Figure AI, Sanctuary AI, and Agility Robotics are redefining what robotic hands can do, and how close they can come to mimicking the fluid precision of human motion. Every fingertip, joint, and tendon in these humanoid robots represents a massive leap in mechatronics. Tesla's Optimus is built with lightweight actuators, compact motors, and tendon-driven joints that replicate muscle tension. Each finger moves with fine control thanks to high-resolution torque sensors and position encoders. Engineers use 3D-printed titanium structures and soft polymer materials to balance strength and flexibility, giving the robot hands capable of gripping fragile objects like eggs while still lifting heavy tools. The Figure 02 robot approaches the problem differently, using electric linear actuators and vision-based feedback loops. Its hands are guided by computer vision models trained on millions of real-world object interactions. When Figure 02 reaches for a coffee mug, multiple cameras track depth, shape, and weight estimation in milliseconds. Its AI instantly adjusts pressure to prevent slippage. The goal is not just motion, but intuition, teaching machines to feel through data. Meanwhile, Sanctuary AI's Phoenix robot focuses on replicating human sensory feedback. The team has developed an artificial nervous system built around sensorized skins. These thin, flexible circuits cover the robot's fingers, providing tactile data for temperature, texture, and microvibration. This sensory layer allows Phoenix to perform delicate work, like sorting electronic components or handling laboratory instruments, without crushing or misaligning them. For industries that require precision and consistency, such as manufacturing and healthcare, this tactile intelligence represents a massive breakthrough. Agility Robotics Digit takes another angle, combining human-like hands with efficient logistics design. Digit's grasping system focuses on real-world usability rather than hyperfine dexterity. Its hands can handle delivery boxes, tool grips, and machine parts with stability over speed. The robot's control software uses reinforcement learning, meaning every grasp and lift helps it learn a better way to move next time. The more it works, the smarter it becomes. What connects all these projects is the blend of AI and biomechanics. The robot's hands are powered not only by hardware, but by algorithms that simulate human learning. Neural networks process thousands of motion patterns, from surgical precision to industrial handling, allowing these machines to refine their coordination over time. Advanced models inspired by the human cerebellum help them adapt to unpredictable real-world conditions. If a tool slips or an object shifts, the AI recalibrates instantly, just like human reflexes. In Tesla's research labs, engineers are combining visual and proprioceptive data, essentially vision and touch, to make Optimus aware of its own body. The robot continuously scans its environment using multiple cameras mounted on its head and chest, while microsensors inside its fingers send real-time feedback on resistance and angle. The result is remarkable. Videos have shown Optimus folding clothes, pouring liquids, and assembling small objects without predefined programming. It's not following a script, it's reasoning through the task. This kind of innovation is fueled by powerful AI models similar to those used in autonomous driving. Tesla's experience with self-driving data gave it an edge. Millions of hours of visual data already trained its neural networks to interpret motion, perspective, and risk. When redirected into humanoid robotics, that same technology enables spatial awareness for the robot's hands. It can predict where an object might move next and adjust grip accordingly, just like a human anticipating a rolling pen on a desk. For Figure 02 and Phoenix, the emphasis is on human collaboration. These robots are being developed not to replace people, but to work alongside them. The design of their hands mirrors that philosophy. The fingers are compact enough to share workspace tools, fit into existing control panels, and even use smartphones. Their control algorithms prioritize safety, Pressure sensors detect when a human hand or arm is near, instantly softening grip strength. In factory settings, this makes them ideal partners, capable of handling heavy or hazardous materials while keeping human workers out of harm's way. To visualize these systems, imagine a sleek laboratory filled with mechanical prototypes, engineers wearing headsets analyzing 3D hand models rotating on transparent displays. Robotic arms flex under bright LED panels as tactile sensors light up in response to artificial touch. Racks of circuit boards hum quietly, while camera modules feed data into neural processors. Every movement of the robot's hand generates new parameters, new data, new opportunities to teach the machine what it means to move naturally. It is a world where mechanics meets neuroscience, and every bolt and sensor inch closer to human capability. The material science behind these hands is equally stunning. Traditional robotics relied on rigid metals, but the latest humanoid designs use lightweight carbon composites and silicone-based skin layers that bend without tearing. Microfluidic systems inside some prototypes mimic blood vessels, distributing cooling liquid to prevent motor overheating. Researchers at Sanctuary AI have tested soft grip surfaces that self-heal minor cuts, extending operational life. In practice, this means humanoid robots can perform repetitive tasks for long hours with minimal maintenance, a key requirement for commercial deployment. AI simulation tools have become essential in their design. Before a single motor is built, virtual environments test thousands of potential hand configurations. Using reinforcement learning, the system rewards efficient motions and penalizes failures, creating a digital evolution process. By the time a real humanoid hand is manufactured, its movement strategy has already been refined through millions of virtual trials. This accelerates innovation and reduces costs dramatically. The benefits of humanoid hands reach far beyond robotics labs. In healthcare, robotic hands are being integrated into prosthetic limbs, giving amputees fine motor control through AI-driven muscle sensors. In automotive factories, humanoid hands handle precision wiring that was once too delicate for machines. In space exploration, robots like these could one day perform maintenance tasks on spacecraft without risking human lives. And in everyday consumer tech, miniature versions of this technology are powering next-generation smart gloves and haptic feedback systems for virtual reality. The human hand remains the benchmark for dexterity. 27 bones, 29 joints, and over 100 ligaments and tendons working in perfect harmony. Replicating that balance in steel and silicon is one of the greatest engineering challenges of our time. But each version, from Tesla's precise actuators to Sanctuary's tactile sensors, brings us closer. The synergy between AI software and robotic hardware is the key. Without one, the other cannot evolve. It's not just about motion, it's about perception, adaptation, and learning. The next step is autonomy. Humanoid hands are now being paired with large language models and multimodal AI systems, enabling robots to understand verbal instructions. Soon, a worker could say, "Hand me that wrench," and the robot would identify, locate, and deliver the correct tool, all in seconds. This fusion of language, vision, and motion is redefining how humans and machines interact. For individuals and industries, the implications are massive. Imagine robots capable of assembling electronics, performing surgery, or aiding in disaster recovery. The ability to manipulate the physical world with intelligence transforms robotics from automation into collaboration. For content creators and developers, these breakthroughs also open creative possibilities, from cinematic storytelling to hands-on demonstrations of AI in motion. The development of humanoid hands is more than mechanical progress. It's a reflection of humanity's own drive to understand itself. Every sensor placed under synthetic skin, every neural model trained to simulate touch, brings technology closer to emotion and awareness. These machines aren't just tools, they're mirrors of human ingenuity. Across labs, researchers continue refining the unseen details: torque feedback loops, adaptive grip controllers, and data-driven learning architectures. The line between human and machine dexterity narrows each year. One day, when a robot hand paints, performs surgery, or builds another robot, we'll look back at these prototypes, Optimus, Figure 02, Phoenix, and Digit, and realize that this is where the transformation began. As the camera pans over rows of humanoid prototypes flexing their mechanical fingers, It's clear that what was once science fiction is now a functioning reality. The humanoid hand is no longer a marvel of imagination. It's a working symbol of the future, where intelligence takes shape in motion and technology learns the language of touch.